Welcome back to my course Aspects of Biochemical Engineering. And last couple of lectures I try to concentrate on enzymes. I told you what do you mean by enzymes and what is the classification of enzymes. Then I try to tell that what do you mean by inhibition of the enzymes. And also that when we talk about the enzymatic reaction kinetics, the major thing that comes with us, that is the Michaelis-Menten equation, is largely used, and how the Michaelis-Menten proposed their equation. Later on, Biggs and Helen, they justified this Michaelis-Menten equation with the help of reaction kinetics. Then question comes how the enzymatic reaction constant like Vmax and Km can be estimated with the help of three different plots. One is lock and key hypothesis, another is proximity effect, and there is orientation effect. The inhibition is a very important part because through inhibition we can apply this enzyme for enzymatic reaction kinetics for the estimation of the different complex molecules. Also it can be used for protection of our health, to kill this certain infection. So this is the different type of inhibition we talk about the reversible inhibition, we talk about the irreversible inhibition, and finally we discussed that that substrate inhibition, how substrate inhibition can be taken into account. Now today actually you can remember that when we discuss about the reactor analysis, we have come across three different type of process. One is batch process, then CSTR, then plug flow reactor. Now those we have solved for the chemical process. Now when we apply to the enzymatic reaction system, how we can determine that batch time, and how you determine the space time for CSTR using enzymes, and how you determine the space time for the plug flow reactor. And finally I want to discuss one problem, and with the help of reactor analysis, how it is possible to find out the reactor. Suppose we want to produce a certain amount of product, and for getting the product and using the same enzymes, whether batch reactor will require less volume, or CSTR will require less volume, or plug flow reactor require that. This question will be answered in one numerical problem. So first let me start with this how we can analyze this enzymatic reaction for the batch processes. So when we talk about the batch process we consider as the unsteady state process. Why? Because that this is the reactor, and in this reactor, this is the substrate you take. So you put your substrate here and put your enzyme here, let the reaction take place, and we can draw the sample from here, and we can monitor what is the substrate concentration at different times, that we can monitor. And when you plot that concentration of substrate versus time, if you plot this plot, then what will happen with respect to time, that substrate concentration will be decreases. Now if you make a slope at different points, then what you will get? You will get minus ds by dt. What is ds minus ds by dt? Is the rate of reaction. How we can express it? Rs. Rs is the rate of reaction, and this is so this is equal to, if you consider this is the first order reaction, this is k into s. So that that had different time. This is T1, this is T2, this is T3, this is T4. So at different time we have different substrate concentration. So this is S1, this is S2, this is S3. So as the substrate concentration changes, your rate of reaction changes. And since the rate of reaction changes, we consider it as the unsteady state conditions. So this is exactly what we want to point out, that batch system is considered as an unsteady state reaction. Now, if you do the material analysis, when you go back to the reactor analysis, we use one particular equation. What is that equation? Rate of input plus rate of generation equal to rate of output plus rate of disappearance plus rate of accumulation. So, this is how this equation looks like this. Now, in case of batch process, there is no input. So, input is equal to 0, output also equal to 0. Now, there is no generation because substrate is consuming. So, what will happen? Two things simultaneously take place, one is consumption and the accumulation. So, this will be like this. What is the consumption? Rate of consumption of substrate, we can write minus RS into V. Why minus RS into V? I explained before also. Minus RS is equal to what? Equal to minus ds by dt. Am I right? So, what is ds? ds is the concentration. What is the concentration? This is mass per unit volume. So, when you do the balance across the whole reactor, this and your reaction take place in the liquid phase only. So, we shall have to multiply this RS with V to consider all the reaction that take place in the reaction mixture. So, this will be like this, and what will be the rate of accumulation of substrate? S into V, ds into V by dt. Now, when you differentiate this, V is constant, the volume of the reactor is constant. So, it will come out. So, it will be ds by dt. So, I can write minus ds by dt equal to V equal to that V equal to minus RS, and then this is as per Michaelis-Menten equation, this will be equal to V max S Km plus S. Now, here we have shown V equal to minus RS, V max S Km plus S. So, this is very simple that we can determine the correlation between, we can make a balance equation across the batch reactor. Now, when we do this analysis of this equation, that I can show you that is like this. Now, what we have? We have minus ds by dt. This will be equal to Michaelis-Menten equation, velocity of reaction V max S Km plus S. Am I right? Now, this what I can do? I can take ds Km plus S, I can write, and this is I can write V max equal to V max S into dt. Now, S I can bring it this side, I can bring it this side, I can rub it here, and I can bring it this side S, and this is dt. Now, if you solve it, what you will get? You can get, I can write 1 by V max, I can take this side, V max I can take common, this will be equal to Km into minus Km into ds by S plus the minus So, I can write minus because minus will come here, and this will be ds, this will be ds by S into S. Am I right? So, this will cancel, and this will be equal to dt. Now, this how we can write? This is V max minus Km. Now, what is this? D ln. This we can write d ln S minus this is ds. This is t. And now, we can do the integration. What is the integration I can do? This is S 0 to S, and here also is 0 to S, and here this is equal to dt. This also we can 0 to t. Now, if you do that, then we will come across the equation what? 1 by V max equal to Km ln S by S0, because this was minus. So, I can always make it reverse, so it is plus, and here it is minus, this is S minus S0. Now, if you plus, then it will be S0 minus S. This will be equal to like this, this will be equal to T, and this is called batch time. So, if you know the value of Km and Vmax, and you know that what is the percentage of substrate consumption is there, then you can easily find it out. Now, one thing I want to point out, sometime we can express in terms of XA, XS. XS is what? The fraction of S that is converted. How we can express is S0 minus S by S0. Am I right? This is fraction of X that is converted. Now, if you want to write this, so here what I can write, this is 1 minus S by S0 equal to XS. So, I can write S by S0 equal to 1 minus XS. This we can write. So, this equation I can modify it as Vmax Km ln 1 minus XS, and then here also we can write in the form of XS, because then S0 minus S equal to XS into S0, XS into S0 it equal to T batch. Now, why we were interested for that? Suppose we want to convert 50% of substrate, just we put it 0.5, X is equal to 0.5 here, and initial substrate concentration, we can put the value of Km, we can easily find out the value of T batch. Now, similar thing has been written here. This is how finally we derive this equation. This is there's a T batch. T batch is coming at will be like this, and this will be little bit problem. This will be like this. So, some mistake is there, you can correct it, and the total batch time will be equal to batch time. Total time of the batch process is the batch time plus downtime. What do you mean by downtime? Time required for taking out the liquid, and time required to clean the vessel, and time required to refill the vessel. That is we consider as the downtime. And what do you mean by that? Downtime means that there is no reaction. So, sometime downtime also we call it idle time. Idle time. What is idle time? Idle time means no reaction take place. That is why we call it idle time. Okay. So, this is how we can find out the batch process, the time required for the batch process. Now, if you come to the continuous process, the situation is little bit simpler, and batch that this process is very easy to operate. You can see this is the reactor, and here I told you, whenever you operate any kind of continuous start tank reactor, first you have to operate it in a batch mode. First you operate in a batch mode, and then let the reaction take place. When you get the maximum rate of reaction, then you continuously feed the substrate and take out the product from the other end. And then when you operate for infinite period of time, you will find the concentration of substrate and concentration of product remain constant, and that we consider as the steady state. What do you mean by steady state? The steady state means when the concentration and different parts of the reactor remains unaltered, that is called steady state. Now, here that the CSTR may be operated under steady state condition. Rate of substrate degradation depends on flow rate and the dilution rate. Now, what is dilution rate? Dilution rate is nothing but F by V. What is F? Is the volumetric flow rate. Volumetric flow rate means volume per unit time. Am I right? Now, this is equal to volume. So, V is the unit is volume. So, V will cancel. So, it will time. So, the unit will be D. What is the unit of D? Time inverse. HRT is the hydraulic retention time equal to 1 by T. What is hydraulic detention time? Hydraulic detention is how long you allow the liquid to resize in the reactor. Now, how we can do the material analysis? The same formula we can have: rate of input equal plus rate of generation equal to rate of output, rate of consumption and accumulation. Now, since we are doing the substrate balance, so in case of substrate, no substrate generation is there. So, we can write rate of input F equal to S0. What is the output? F into S. F into S is the output. You can see this is the input that we have. And what is the consumption of substrate? Minus RS into V. Now, if you write this equation, you can write this equation in this form, that F this equation we have this form, and this equation we have if you look at this equation, the F0 into equal to Fs plus minus Rs. Rs is equal to velocity of reaction. What is velocity of reaction? This you can express as Vmax S divided by Km plus S. Now, this is exactly what we have written here, and so this is final expression will be like this, that a V, the V I can take it this side. So, this will be D, the dilution rate into S0 minus S equal to Vmax S. So, this is we can. So, this is equal to this, and since the dilution rate that is like this. So, 1 by D is the hydraulic retention time. So, from that I can easily find out that what is the space time required in this reactor. How we can find out? Let me show you this. Suppose we can write this. This is equal to D equal to, I can write D equal to B max S divided by Km plus S. Am I right? Now, this is divided by 1 by S0 minus S. And what is this? This is equal to, I can write this is the dilution rate equal to F by D. And 1 by D is equal to what? The HRT. And this is actually HRT is nothing but space time. Space time of the CSTR. That means how we express tau CSTR. So, how you can write the expression? This is the inverse. So, how we can write the tau CSTR? Tau CSTR will be equal to S0 minus S divided by Vmax S Km plus S. So, we can easily find out this tau CSTR. Now, let me talk about this plug flow reactor. Now, plug flow reactor, I told you it is also can be operated under steady state conditions. That but plug flow reactor, plug flow, what I told you that plug flow is something similar to the piston flow. What do you mean by piston flow? Piston flow is the ideal flow. Suppose there is the piston here, and when it piston goes, we assume the velocity across this cross section is uniform. But actual case, when liquid pass through any kind of tube, then we have gradient of velocity. We have like this, we have gradient of, as the liquid close to the wall surface, then the velocity will be reduced. Why it is reduced? Due to the friction between the liquid and the wall surface. So, there is the friction, and due to the friction, the velocity of the liquid will be reduces to a great extent. So, but that is that in case of piston flow, this is considered as the ideal flow, because we assume there is no velocity gradient across the cross section of this. Now, in a true sense, when you have laminar flow, we have velocity gradient across the cross section of the tube, but when you laminar flow tends to the turbulent flow, then velocity gradient will be minimized. Now, how you can do this analysis of the reactor? Here this is, suppose this is the reactor that we have, this is the input one end. I told you in this there is no back mixing, no axial mixing is there, but there will be radial mixing. Suppose radial mixing means, suppose this is a tube, and here you can have radial mixing. Circular there will be mixing, but there is no mixing in the axis, that is actually taking place. Now, for analysis this reactor, what do? We take a differential segment. This is the differential segment where this is the F, that is the input, and what is the F is the flow rate in, F is the flow rate out. But substrate here, substrate concentration is the SZ, here SZ plus del Z. Del Z is the width of the particular differential unit. So, I can write F into SZ, that is the rate of input of substrate, F into SZ plus del Z is the output, and minus RS into A is the area, cross sectional area. If you multiply it by this into Z, you will get the volume of this. This volume is, if you assume to be del V equal to nothing but equal to Z into del Z into A. So, I can write it as del V is equal to del Z into A. A is the cross sectional area. So, this is nothing but the volume of the reactor, and if you solve it, it will come in this particular form. And then we again if we do the integration that of this the u versus u, what is the u? Is the velocity. U is the how you calculate the u? Because if I assume that the flow rate, the F is the flow rate, am I right? F is the flow rate, and this is volumetric flow rate. You see that what you can do, that this is the volume that you have, and this is u. U is the what you have. This is the volumetric flow rate, and this is the area. This is the volumetric flow rate, and this is the area. Volumetric flow rate is the volume per unit time, and what is the area? Cross sectional area is centimeter square, or per unit that length square. So, this volume is the length cubed. So, this will cancel, will be length. Length by time is equal to the velocity. So, this is exactly that we have shown here. And then if we do this, this will be equal to u into limit this can be integrated, and this equation will comes like this. And finally, we come across this. This is the equation that we have, that is u into ds by dz equal to Vmax s by km plus s, and this is equal to 1 by u, where that dz equal to this one. And finally, that we have this equation L by u equal to 1 by Vmax, and by this now I want to point out L means length, am I right? And what is u is the velocity, length per unit time. So, what will happen, that if you this length will cancel, and this is equal to nothing but tau plug flow reactor, and this is 1 by Vmax km is 0 is, and if you look at this equation, it is same as compared to the batch process. Batch process we have the similar expression with that. So, that is why we have written the batch time the space time of plug flow reactor same as required in the batch process for a particular reaction. Now, I want to show you the solution of a particular problem to make this things very clear, because the final objective of the reactor analysis is just to find out the volume of the reactor. Now, this is a very interesting problem. The glucose is converted to fructose by using glucose isomerase enzyme. Initial glucose concentration in the reaction mixture is 200 grams per liter. Degree of conversion is 60%. Calculate the volume needed for 10 kg fructose production. Now, the enzyme we use glucose isomerase. What is the happening? The glucose is converted to fructose, and fructose is 10 times sweeter than glucose. So, this is used largely in the confectionery industry to convert glucose into fructose. Now, with this particular reaction, we want to find out which reactor will be good in the batch reactor, CSTR and plug flow reactor. And these are the different values, that is Vmax and Km value and other value this given in the problem. Now, the basic stoichiometry of this equation is like this: 1 mole of glucose produces 1 mole of fructose. This is the stoichiometry we have. Now, in the batch reactor, what we have already derived this equation, am I right? That in the batch we have this. So now Vmax value is given here, Km value is given here. I have shown you Xa is what is Xa? Xa is the fraction of substrate that is converted. This is S by S0. Am I right? So I have shown you this. So if you put this value directly, you will get this is the volume of the reactor is coming 2.3 hours. And then we can find out the total time. What is the total time? The batch time plus idle time. Idle time is 4 hours, so total is that. Now, when we want to calculate the volume of the batch, first we shall have to find out how many batch you have to operate per day. This is 3.8 batches. So, how much product you have to produce? 10 kg of fructose. The per batch how much product is to be produced? You divide by 3.8. So, you will get 2.63 kg of product. And for this product, how much substrate is required? Glucose is required 2.6, because 1 gram of glucose produces 1 gram of fructose. So, 60% conversion of substrate is there. So, you can easily find out how much glucose is required for the batch process. Now, if you know that how much glucose is required for the batch process, and this is the initial concentration of substrate. The concentration of substrate was 20 gram per liter, and this can be expressed as 20 kg per cubic meter. So, this is exactly what we have done, and this is coming at 0.022 cubic meter. So, what is the volume is coming in the batch process is 22 liters. Now, when you come to the CSTR, tau CSTR, that we have already derived this equation, S0 minus S minus Rs, then put this equation in this form, put this, we find this, the time required for the CSTR process 2.36 that hours. Then we find out that how much product you have to produce? 10 kg per day. Am I right? 10 kg product per day we have. So for the 10 kg product, how much substrate is required? 60% conversion of substrate. So you divide by 0.6. So it is coming 16.767 kg per day. So per day, that means how much substrate is consumed per hour? You divide by 24 hours, because one day is 24 hours. So it is coming 0.7 kg per hour. So how much actual substrate is required? This. And what is the initial substrate concentration? 200 kg per cubic meter. And what is the volume we get? This is about 3.6 into, this is the value, this is the flow rate we get, and if this flow rate, if we multiply it by CSTR, tau CSTR, we will get the volume, and volume we are getting 8.26. So from this we can conclude that when you operate the continuous process, the volume of the reactor is drastically reduced. that you can easily find out from these calculations. Now, similarly, we can do the calculation for the plug flow reactor. We have this equation, and this is similar to your batch process. So, same time you will get, but only thing is that the conversion of this with respect to this that similar to as CSTR. So, we find out how much substrate is required, same amount of substrate is required per hour. This we can easily find out, and then flow rate, the same flow rate what we observe for CSTR, same flow rate we will get. Now, this flow rate, if you multiply it with tau's plug flow reactor, we will get the volume. So, in short, if you find out that if you summarize all the things, then what we will get? We will get the volume in case of batch process is coming 22 hours. In CSTR 8.26 and plug flow reactor 8.07. That means our design should be plug flow reactor, because if we recommend what reactor is suitable for this process, we should go for plug flow reactor. So, what I conclude in this lecture, that this is vital in the sense that how this reactor analysis can be applied in the enzymatic reaction system. And we here also we try to analyze both batch reactor, CSTR and the plug flow reactor, and we have taken and we try to find out the mathematical equation with respect to T batch, with respect to tau CSTR, with respect to tau plug flow reactor. And once we have that, then we can easily find out for producing a certain amount of product, how much time is required for the batch process, how much time is required for the continuous CSTR and plug flow reactor, that we can easily find out. And once we know the time, then we shall have to, in case of continuous process, we shall have to find out the flow rate, then we can find out the volume of the reactor. And when we compare all this, and whatever which reactor, which process having the lower smaller size, that will be our design of the reactor. This is how we can design the reactor. Thank you very much.